Yes, you're right. But with the whole thing crashed, and not because of the internet. So I don't know. I don't know. I'm not a IT professional. Maybe it's okay. Well,
Yeah.
we shall soon start. Bum, 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 bum. Yes. Okay. Okay. So I'm going to make a short introduction, and we will you will be able to make your presentation, Brian. So
Okay. Yeah.
about the NAS. Well, thank you very much to all of you being there for this second class, which is dedicated to quantitative finance made accessible. And today we will talk about the stochastic process, which is really a paramount thing to understand in order to get the grasp of all those models about modeling, hedging, pricing, and so on, especially options. And I thought it was a good idea to have a professional guest speaker, Brian Lowe. I've worked for more than 20 years in the financial industry, and he was in the asset management, asset liability management, liquidity, and so on. And he knows a lot of things about option pricing. And in fact, we will start at the end, in fact, because we will talk about the mini case first, and after that, during 15 minutes, Brian will talk about what he thinks about Black-Scholes models, and make the bridge between the theory and the practice. And after that, for 15 minutes, and there will be 15 minutes of question and answer session. And in half an hour, so I will, go through the theoretical stuff, going from the symmetric random walk through the arithmetic Brownian motion, geometric one, and after that we make a short conclusion about the Black-Scholes models. So now I'm going to hand over the mic to Brian, and he will explain to us what he thinks about the stochastic process applied in his day-to-day professional life. Okay.
Okay.
So Brian, when you want.
Yeah. Thank you, Florian. Can you all hear me?
Yes.
Okay. Can you all see the screen?
Yes.
Can you all see the screen? Can you see all the? Okay. So I actually put together several slides, right, to run through some of the random thoughts, right? Since the geometric Brownian motion is actually a random walk. So in some senses, it's also my own random walk for the next 15 minutes. Okay, so it's a sharing section. So no hard technical details. I'll probably tell you a bit more about we live and breathe, right, with derivatives. At least for me, for the past most 25 years of my career in risk management. And okay, so let's move. Okay, so I'm Brian. So I'm just can skip this very quickly. I work in I'm in Singapore now. I've been staying here for 20 years. I work for a sizable bank in this part of the world, 500 billion US balance sheets. And the markets business, including derivatives, makes a budget of around, say, more than 2 billion US a year. Okay, so you can think about sizing it. And before that, I worked with French banks and American banks when I started my career in finance. And I'm doing a little bit of teaching, and I am running my own independent consulting business. So I just hope that we have a chance for the next few minutes to talk about use of geometric Brownian motion in derivative risk management, covering pricing, valuation, risk measurement, and a bit of portfolio management. And to start with, probably this is a conclusion as well. And there are a lot of pitfalls and weakness and attacks on geometric Brownian motion. It doesn't depict factors. It doesn't actually depict volatility clustering. It doesn't depict a lot of features in financial time series or spot FX rates, equity prices, interest rates, etc. But in spite of all these attacks, it's still one of the most efficient tools, right, in pricing derivatives. Okay, especially for foreign exchange, equity, commodities. Interest rate is a little bit more complex, and especially when the spot process, right? It could be a stock price, could be an FX value, dollar euro, for example, Swiss francs yen, for example. And when the spot processes can be treated as continuous motion, and this is something that is, you learn it in your high school, right? About gas motions, the discovery of boundary motions under the telescope. It's all about continuous motion. Okay, we don't talk about jumps. We don't talk about choppy processes. It's something simple. It's continuous, but it's actually not differentiable. I mean, there are other features as well studied, probably more than 100 years ago, or on Brownian motion. And for the applications to the spot prices or in financial markets, we talk about the relative return or log returns of that process being portrayed by Brownian motion, and that's why we call it geometric Brownian motion. I mean, that's how you link it. A slight remark is we have to, while we most of the time actually focus the application of geometric Brownian motion to derivative pricing, etc., of products. The pioneer is another pioneer is actually Bachelier. Right? I mean, it's a French gentleman that actually started with not the geometric Brownian motion, but arithmetic Brownian motion, and try to depict the asset price movement, etc. I mean, of course, the biggest difference is with geometric Brownian motion, the prices won't get negative. I mean, that's actually quite important, right? Very, very important point. Okay, so it's used. It's still used especially when a new asset class is traded. I mean, in the previous slide, actually, I add a little tail at the very end in the last sentence. What about cryptocurrencies? What about assets that have very, very choppy prices, and you wonder whether a continuous stochastic process is actually appropriate, right? You have, again, a very long story being studied on that. I mean, the people still publishing paper on that, but it's not widely used, I would just say. So in terms of the product development with the new asset classes coming in, you start with trading on what we call the cash or the spots, right? Then once you trade a lot of that, you start to trade futures. I mean, the most famous one actually agriculture ones, right? You trade futures on grapes, you trade futures on pork bellies, you trade futures on corn, etc., etc., etc. Of course, the futures markets allowed speculation as well as hedging strategy to be deployed. So that's the first type of derivative away from just trading spots, right? Of course, futures are traded in exchanges, but you can have agreement between two parties to trade. We call them OTC, over the counter. And then you don't need geometric Brownian motion for pricing futures yet. But once you actually get into options, plain vanilla options, and more exotic and complex one, then it enter naturally. The use is big, right? Because it allows speculations using options, because intrinsically it actually allows leverages, intrinsic leverages, and then to allow customer hedging and price discovery. And then we will soon realize that the volatility used to price option is actually implied volatility, not historical volatility. I think that's very important. And on top of that, financial engineering allowed packaging of these components into structured products, FX structured products, equity structured products, credit structured products. And the exchange also would come in to compete, right, with this OTC market by providing listed products, right, to expand the participation of players, right, into taking positions, long, short, or whatever, on products, mostly derivatives. Right? So the market risk and management topic as a whole is not just pricing, right? Because you need to price. Okay, so you want to price something as what's the value of Apple? Okay, it is €1 today, or 50 cents euro today. You want to actually have a call option on the Apple in 3 months. You can actually buy it at 70 cents. I mean, that's a plain vanilla call option. I mean, this is very easy to understand and to explain, right, to people. But then to have to develop the models, and that the most common approach is actually to use geometric Brownian motion and with some of the key assumptions to get into the Black-Scholes equation, okay, for the option, and then you have a solution, okay, numerical solution. In the best case, you have a closed form formula, and in other cases, you need other numerical values to extract the value, the present value of the motions. And we also need to know not just the value, but the value of the option when the underlying drivers move, right? It's affected by risk-free interest rates, affected by volatility. What if the strike actually changed, for example? I mean, all these, and time to maturity, all these will actually change the value, right? Even if you just look at the Black-Scholes formula of the option, right? So the sensitivity to this risk driver, collectively, I don't know who actually invented that. I call them Greeks, right? And I think that, and that's why we have delta, which is sensitivity to spot. Gamma is a second derivative of the spot value of the option, right? With respect to spot. Vega is the value of the option with respect to the change in volatility. Okay, anyway, so with all these, there's an industry, probably first of all internal in banks, and somehow could be external, because there are some companies are actually tasked to carry out this job called model validation. You probably actually heard a bit from last week, right, on Martin on the work. I mean, I think major work on model validation is actually required, right, to give confidence for users that the models are properly built, developed, coded, run, and returned desirable results, for example. And then we enter into, once we have the way to obtain option values and the sensitivities, then we start thinking about risk. What's the market risk? value that drops, value that increase. What drives it? And when we trade derivative, we have counterparties, right? So we trade derivatives and the value of the derivative goes up. It means counterparty is losing money. If it's can't top up, pay, or whatever, in defaulted, we have to replace the contract, and that's a cost, that's a credit loss, right? So that is credit risk. So derivatives have market risk, which is price risk of the product, and counterparty risk, right? Derivative counterparty risk, which is a credit risk. And somehow, as we all know, for plain vanilla products in the FX market, in the equity market, it becomes, the Black-Scholes formula becomes a quoting convention. You ask a broker for a quote of, dollar yen, 3-month dollar yen call strike at the money for, I don't know, 100, 150 today. He would just quote you in terms of volatility, because that's the quoting convention. Everybody agree to use the Black-Scholes formula to actually convert back to values and whatsoever. Right? So that's another important use, right? That's a direct derivation of geometric Brownian motion through Black-Scholes equations formula, right? And then you have other measures, the value risk, vol, expected shortfall, and some of these will enter into regulatory capital and calculations, right? For banks. The last bullet is just some information from the BIS, the Basel International Bank of Settlements, where they have a half-a-year OTC derivative volume report coming out. And so this one is for last year, so it gives you a sense from end of 2022. The total nominal values of interest rate derivative is $490 trillion US dollars, FX 108, credit spread, credit derivative 9.9, equity 6.9, and then the rest could be commodity, etc. So the total is 618 US dollar trillion. How do you compare with the total GDP of the world? Number one, it's not comparable because this number is nominal. And we all understand, right? In derivative, we don't talk about nominal. Nominal means nothing, except probably for digital options. But it's not risk, right? But it just gives us a sense. Okay, so next I'll talk about a bit more that the Black-Scholes formula, Black-Scholes equation and the formulation is quite universal. And so it's not just applicable to plain vanilla European called or put. It can actually use it, okay, provided you find a way to solve it, right, for American options. There are more complex options as well, barrier options, single barrier, double barriers, one touch, digitals. I mean, there are variations in terms of the conditions, both we call it initial conditions or boundary conditions, right? Just applied to the Black-Scholes equations. So numerically, if you can solve it, and sometimes if you're lucky, like barrier options, you can have a semi-analytical solutions with no smile volatility. Then you actually can make the computation a bit more efficient, right? But it's still I would say that the de facto choices when you actually start. Now, there are more variants of geometric Brownian motion, right? I mean, if you look at the Black-Scholes equation, right? Okay, for example, there's another story, a long story to tell, right? What is volatility means, right? Is it if it's really a function of spots and the strike and the maturity, then it's a totally different story in the derivations, right? So again, but this is history. This is a 30-year-old development. So I'm sure you hear more from Florian, right? Subsequently, when this happens. So again, the modeling part doesn't actually stays the same. I would just say, but it just provides something very quick, very offhand, right? Of course, to have some sense, right? And so I'll just list down the list of action standard. You have a Baxter's equation, initial boundary conditions, you have to calibrate volatility, and then the numerical approach can be analytic, can be semi-analytic, can be trees, well, binomial, trinomial, can be PDE. But I can tell you, started probably 15, 20 years ago, if you have a portfolio of derivatives, serious portfolio, the only method you use is probably Monte Carlo simulations. Why? Because the value of the derivative, as you will know or have known, is actually just expectation of a function, right? Under certain probability distributions. And finding expectation in Monte Carlo simulation is just easy, right? You just simulate a lot of problems, compute the average. So this is one way of explaining why Monte Carlo simulation is useful. No, because in a way, it's just compute expectations of a probability distribution of a certain function. Anyway, so hedging is important, right? It's not just a theoretical value of taking derivatives of whatever you have, right? To spot or volatility or interest rates. Reality checking is important because if you're long a call, you have to short some cash, right? Short a spot, right? So anyway, it might be done. It could be done. It could not be done, right? In US, you still have to observe the uptake room, and in some markets, the exchange will actually tell you which stocks can be borrowed and short and which cannot be, right? So again, it's a total different story. I mean, if you actually buy a call and then you cannot short and flatten the delta, you're actually doing betting. Okay, so again, should it affect pricing? Of course, but how? I mean, those are actually reality constraints that will actually affect traders to think of whether they will actually use, even for plain vanilla options in a particular market with a lot of constraints, whether they will just use it. Okay, and then you say, no, I can't use it. It's just too cheap, right? Because I cannot manage, right? So then do you double it? Do you triple it? Will you make it safer? I mean, those are the reality questions we have to face from time to time, right? And then most of the time, or sometimes, and then you have to think about, if you can't hedge with stocks, how about you hedge with index futures, right? Index futures, you can long and short, right? That's the first thing you can do. But of course, there's a lot that we call basis risk, right? Between an individual stock movement and the index movements, right? So they will create a lot of noise in the P&L if you actually use an index to hedge. But there are ways to articulate, right? So anyway, and then do you want to actually manage or increase or decrease some of the exposure arising from your derivative portfolio, right? If you want to hedge, increase or reduce your gamma risk or vega risk, and how? And once you get into exotics, I put the word light. Couldn't help it. Like Barry options, the hedging strategy becomes less straightforward because the Barry option means the value of the options will jump. It likely jumped when it actually hit a certain level when the spot value. And traders hate jumps most of the time because they can manage, right, the value. They can lock in the value, right? Of course, if your jump is always on your upside, if anything happened, well, so be it. Life is not that simple because it's most of the time your counterparty that take the advantage. They ask you whether you want to actually warehouse that risk. Anyway, there's a little story on that. And then the risk measurements will come in as a consequence for the risk management, etc. So again, so those are the few, little points I actually put down to share with everyone on the use or applications, right, of geometric Brownian motion and the Black-Scholes equation and would add to any any banks and serious banks have option portfolios, right? With instruments, they're just showing up today, everywhere, every bank. Thank you.
Thank you, Brian. Thank you very much for this very insightful, practical, example. Any question? You can ask your question, drop your question ideally in your comment section. I read them, or Brian will read them, so that it's not too noisy. Please use the comment section if you ask. Write them down in the comment section or the chat. Sorry, it's comment section. I didn't say on LinkedIn comment section, and in the chat room. No question. I have a question. Brian, it's really interesting because I read on your slide about calibration, volatility calibration, and you said when you don't have implied volatility, we are talking about option. When you don't have implied volatility or no way to I don't know, interpolate that this volatility, you use historical volatility. And in one of my articles on LinkedIn, I trade only cash instruments. So I trade US stocks, and I'm pretty fond of, like I told you when we met to organize this session, I'm pretty fond of volatility. And I trade hyper volatile stocks, and I use historical volatility. And in fact, I'm pretty, I have a pretty quantitative approach, but I don't use stochastic calculus to make my trade. But it's another story. But I love historical volatility because it's, to me, and I backtested my system for so many years, that it's a really good indicator of future next volatility. But it's my it's my stuff. And you say, oh, and when I was writing this article, I said, when you can use to backtest your system historical volatility, and a guy fond of option and so on said, no, it's not true. You use implied volatility. And I say, yes, but you need historical volatility, okay, to a certain extent. And yes, implied volatility, we are obsessed with implied volatility. But so my question is, what about calibration, and how do you assess that historical volatility when you don't have implied volatility to adjust your your model to be well calibrated? How do you do that exactly? How do you incorporate historical volatility when you don't have implied volatility?
At least two levels of answers. If you ask a risk manager that actually need to run value risks, have even scenarios, right, or on the portfolio with this particular option with new underlines. That's one question. You need historical volatility. I think this one has been long debated, right? What kind of volatility you use in value risk, in counterparty risk, PFE, Monte Carlo simulation engine? The answer is always, well, if you are Q, you ask the question, do we use P or Q? Florian was like, is it P or is it Q?
Yeah.
And I think for risk managers, we always like historical or physical volatility. Oh, okay. You ask a trader.
P and Q. P is a physical measure, real measure, and Q is a risk control measure. So it's a really paramount to assess, and it's why you have theorem to go from one to another and so on. So for those who do not know.
Yeah, you need. Yeah. Well, anyway, so but I think for traders, it's always something very practical concern. The first question they ask: are we buying or selling? You're buying, you just add. I mean, provided your option has positive vigor, right? The value increases with volatility. If I'm short, of course, I actually take out something, decrease the historical volatility. And for some markets, it's actually quite, I mean, it's very easy, right? Because when you need implied volatility, you need a relatively liquid and deep option markets to infer back, right, from option prices to volatility using the Black-Scholes formula. So, but it's very clear, right? If you look at G7 currencies on FX options, the historical volatility, the realized volatility is actually quite close. Well, I mean, they always compare with with the implied, right? So so G7 probably never actually get beyond 10%. It's always range between 7 and 10, whatever, with exceptions. Equity is a guess, right? So because I see a question on VIX, so some people might say, well, we just read off from VIX and see up and down adjustments, right? Maybe. But again, from a more theoretical point of view, the VIX is itself, the variance swap itself, and this is a classic textbook example, textbook chapter, that the value of the variance swap is essentially a linear combination of plain vanilla options at the same maturity, right? So it's the linear combinations, whatever. So it's not that bad. But
yes, there is a question. Maybe you can respond to Fa.
Okay. So I don't know. I see. There's quite a few. I definitely skip the one on my birthday. So thank you very much. Okay. So I mean, there are quite a few. I mean, I can answer something simple. For example, your moneyness, is it by delta or by strike? By actual strike value, right? And this is the biggest debate between FX option traders and equity traders, because you ask, and at the money, dollar yen 3 month and at the money call, what's the strike at the money? Well, at the money, of course, it's at the money forward, right? Florian knows well enough. When you trade FX options, at the money is at the money forward, period. Equity guys will argue with you till cows come home. No. What forward? I don't know the dividend yield. I don't know. I mean, there's so many things that will affect the forward. I don't care about the forward. I care about the strike. Today is now trading at 51. Well, at 51 is the at the money strike. And of course, there's a lot of story about the volatility scheme, right? When you actually move from day to day, when you move the spots, whether the shape of the volatility curve and surface will translate. Right? That's another another story. But that's actually convention, and many systems will allow you to choose, right, your volatility grid. Okay, maturity and strike. Whether is it really by strike or it by delta? Question. Wow, that's one. Anyway, so an interesting question. If that the
sorry, I think I interrupted. No, please continue. I have one question, but I'll get there after you wrap up. Sorry. So my question was again on the volatility side, right? So what happens? I mean, let's assume we are in 2014, right? So the Facebook stock has not launched. In that case, you don't have implied, you don't have historical. In how would you kind of arrive to a proxy there?
Yeah. So classical interview question for getting a risk management job. You make it up, of course. And the way to make up spot prices is very simple. You have an IPO stock, right? You trade on the first day. Where do you actually get historical volatility? Okay, if you're running a historical simulation value risk, where do you actually find past 2 or 3 years of spot returns, right, to formulate your scenarios? You can't. So the rule is general that, I mean, some banks will just say, oh, you just take the index. Not too bad. The other, if you want to do a little bit more work, or you want a colleague to do a little bit of work, or maybe it's you, then you say, oh, do we know, can we pick a similar stock in the same market, in the same sector? It's very similar, so maybe you can use it, right? Okay. As a proxy. Okay, so it's really about risk measurement, so we're not as precise. Okay, the requirement on precision is not as bad as pricing. Okay, for pricing, for you are talking about 0.1% move, right? In valuations, FX, equity, right? Big thing, 1 cent. For interest rate, guys, they're talking about bips, okay? 5 BP is significant, right? Anyway, so I'm just saying that you don't have it, you find some logic to cook it up. Okay, so implied, as I said, right? You don't have implied, then you cook with maybe you use either you use the index implied. Now, index implied versus stock implied, there's a big story that people actually doing a lot of stuff. Okay, or strategies on it, because okay. Anyone know what's the cash and carry trade? Push up. Well, not Florian. Cash and carry trade is very simple. You want to find capture the basis between the basket of stocks and the futures, and you know they will converge. And the day when the future actually fixes, of course, how it fixes, there's a still basis, right? In some markets, the futures fixes will be average of a full day trading every 5 minutes or whatever. And that's definitely is not the end of day as well. So we still have some basis, but in general, if we leave some of these, the cash prices and futures prices converge. And that's the basis of what you call cash carry trade. Very heavy cash required because you have so many stocks to mimic the futures. Now, for other products, especially volatility, there's no guarantee, right? If you buy every single, say today, at the money forward for the next expiry of the CAT index components versus a CAT option, there's no relationship between the two. Sometimes people that have a firm belief to put in something called dispersion trade by forcing a weight on the individual single stock option by its gamma. I saw those trades and didn't work very well all the time. Well, anyway, so probably I'm leaking too many industry secrets already.
Okay, Brian, we have to stop now. Really, thank you very much to share your experience about it's modeling, hedging, and how to summarize what you said. There is no perfect hedge, and you have to take into consideration the kind of asset you trade, the purpose of your exposition to such an asset, and you have to use implied when you have it, or historical, and there are many parameters, and it's really really interesting. So we have to stop now. Your part, you can remain with us if you want, Brian, and thank you again. Now I'm going to share my screen, and we're going to go through the theoretical stuff, okay? And I will share. Do you see my screen here? So, well, it's stochastic processes in finance. So it's the building block of quantitative finance. And in fact, we have stochastic. Where does it come from? It comes from Greek, which means in fact conjecturing, making a guess. It's what it means, stochastic. But when you see all those math formulas, you just ask, what is really the meaning of all this? How can you make the bridge between the theory and the practice? So, I read some, you are about 700 to register for this series of, classes about, quantitative finance made accessible. And I read all, the form, the forms you filled, and every time, implicitly or explicitly, you ask for more, insight about the bridge between the theory and the practice. So my aim is to help you understand this, complicated stuff, because remember, mathematics, like physics, are a tool to understand. If you don't understand the intuition behind the most difficult, mathematical formula you could, intellectually understand, it has no meaning, because you want to make money as a quant, and to make money as a quant, you have to make money for your companies, okay, your company. So it's good, Math is a really useful, tool, but you have to understand your intuition behind the math. Okay, so a stochastic process is what is a sequence like it's written here of a random variable. So there is in stochastic process there is this kind of random experience. You don't know uncertainty. Volatility is everywhere in the market and in life also. You take risk. There is the opportunity cost, there is the real cost, there is the implicit cost, there is explicit cost in every choice. Okay, it's the same in the market, and you have to understand that we are in a highly unpredictable world, and you have to use the probability rules and models in order to, in fact, not forecast but make a guess about what the future price will be in 1 day, 2 days, 3 months, 6 months, and so on. Brian talked about there are contingent claims, and there are also futures and forwards. It's less complicated because there are not all those stuff like Greeks and variables that you don't really it's hard to control. And it's why we talk about option and not forward on stocks or future, because it's really easier to price, because there is a future obligation to buy or sell an asset in the future at a given price on a given asset. Okay. And there are many analogies you can make. You can use the stochastic processes to assess, the stock price, the future stock price, and also or the option price, your future option price. But you can also find it in the weather forecasting. We are good at it now to forecast the probability of rain tomorrow or in 2 days or in 3 days. But there is still room for uncertainty. But we have to get models to be as much as possible be able to give a guess that we can rely on. If we forecast rain tomorrow and it's sunny, it's no problem. It's if you're wrong one out of 10 times. So we don't look for certainty. We look for on average, we will be correct to forecast the weather tomorrow. So it's what we want to do when we forecast a future price of an option price and so on. Okay, so the stock price is inherently unpredictable, and there is uncertainty is also something you have to deal with when you trade stocks, even cash. I trade cash stocks, and I have to deal with volatility, And but when you trade options or you want to hedge your portfolio of options, you have to deal with many different variables, the Greeks and this randomness, which is about everywhere. And we use options to it's an insurance product, and it's we need insurance company use options, banks use options. We use them in many fields, and we also use stochastic processes in what? Portfolio management, trading, hedging, risk management. There are many fields where we need to understand stochastic process. So we're going to start with the random walk, and we will start with the symmetric random walk. The random walk, I could have, taken an example of, tossing a coin. You have, the same probability of getting a head or a tail, but in a random walk there is a walk. So I'm going to keep the original idea behind that, and we are going to imagine a walker who walks, and we don't know where he will be in the next step. Okay, but there is the same probability that he will make a forward move or backward move, okay, or a move on the left or a move on the right. So it's what a random walk means. So you have a randomness, and you can measure that step by step, because you can you don't know what the next steps will be, but the steps are always the of same some length. Okay, we will talk about non-symmetric random walk, and everywhere we are faced with non-symmetric random walk, but it's the first step toward the famous Blackwood-Scholes model. Okay, so in the financial markets, we use the random walk hypothesis to assess the behavior of asset prices, because asset prices and stock prices suggest that they follow some kind of random walk. We don't know where the price of Tesla will be tomorrow. We know that it closed at I don't know 120 yesterday or whatever, but what is the price of tomorrow's Tesla stocks? And what about the option? Okay, it's what we are interested in. And again, we have this kind of picture of this worker always making a forward or a backward or move on the left or the right of the same size, the same length, which we don't know where it will be the next step. So it's what randomness means. Okay, you have alternate or other kind of random walk like the Levy flight, where you will Levy, it's about jumps, and it's about different size of steps that you really face in the market. It's not always the same volatility. You have the up move, you have the down move, but you don't know. You have a volatility of 10% on average, but sometimes it will be 20%, or sometimes it will be 30 or minus 20. I don't know. But on average, the volatility will be 10 or 15%. Okay, so it's pretty. It's just to start with a stochastic process. It's a good thing to imagine a random walk, because you can easily picture that. Okay. What is the mathematical representation of symmetric random walk? You have a probability of 50% of being at step n+1 forward move, or backward move n-1, which is the same probability to be in that state in the following step. Okay. So the properties of the random walk is the symmetric random walk. The mean, the expected position after n steps, is 0 because of the symmetry. Because on average, you will make 1 meters forward, 1 meters backwards. You don't know the distribution of the backward moves and the forward moves, but you know that on average, since it's the same probability to make a forward move and a backward move, on average, the expectancy or the expected position of the walker at the nth step is 0. It's really important, because you will have the same property in arithmetic and geometric Brownian motion. So remember that. The variance, which is really really important to remember as well, increases linearly with the number of steps. Specifically, on the one-dimensional random walk. What is a one-dimensional random walk? It means that, in fact, you follow a line. You follow a line, and you can move, around this line, and it's the variance of your moves are linearly linked with the numbers of steps you will make, and you will see in the geometric Brownian motion that the variance is time. It's time. So it's, again, you have the you have here the properties that will remain the same in the different stochastic models we will go through today. Okay. Another property is the stationary increments. So what does it mean, stationary? It means that the probability distribution of the walker's position won't change over time. The probability distribution, in fact, doesn't change, which is pretty interesting, because you don't know where you will land at the next step, but still, the increments, so the difference between two steps, two positions, between two time steps, follow a probability distribution. So it's great when you want to trade or hedge your position, because you can still rely on probability, even though you just have this random parameter that you will not be able to get rid of. Okay. Two other properties you have to remember. I wrote a short article yesterday or 2 days ago, I don't know. Markov property, memorylessness. Markov property, what does it mean? Each step is independent of the previous step. Okay, it doesn't depend on it's not because you went at you were on this position, of 10 steps ago, that it will have an impact of your position now. So it's pretty interesting. It means that, in fact, you can't, in fact, rely on the former position to assess the position now, and especially the position of the next step you will have. Okay. Martingale property. You don't know about martingale. Martingale property is about this casino. No, it's not exactly the casino, but it's a way of dealing with your losses in a casino. So when you bet every time the same the same amount of money, and but you will no, you don't bet every time the same amount of money. You will double your bet every time you lose. Okay. And even though you do that, but the casino won't let you do that, because the casino could go bankrupt. But even though the theory said that the martingale property means that even though you bet will increase, double in size every time to recoup your former losses, you will still be flat, because even though you will make a huge ton of money, because you double your size and you will eventually win, okay? Since there were many losses you have to deal with, in fact, you will be flat. So martingale property is a fair game. That's why when you say anti-martingale strategy is like trend following, you cut your losses short, and you let the upside move, or your gains, you follow the trend, so you truncate the downside and you don't truncate the upside, so you have an unlimited theoretically unlimited upside, and you truncate the downside, so you are in you are potentially a positive gain expectancy. You understand? So martingale property means that whatever you do, in fact, you will not make money. Okay, so more formally, considering the symmetric random walk, it means that the expected value of the process at the next step, given all the past information, it's why we talk about filtration, it's all the information you have accumulated until now, is equal to the current value. Okay, so the expected value here, considering all the preceding motions, will give you the current situation, the current position of your stock, of your walker, of your particle in a fluid, whatever the stochastic process you end up with. Okay, so here we are going to you can visualize the symmetric random walk. It was from your Python script, and you have here the number of steps. Okay. And you have the position here, okay? So you have the number of steps here, and which increase with the time, and the more time passes, and the more the motion will accumulate in what we mean this quadratic variation. The more time passes, the more you will have rough pattern of your move. Okay. Here there is another simulation, or another way of picturing the random walk. Is this maybe Brown, who first discovered this particle in a fluid, following a random move, is what he saw, maybe kind of move when he realized that this Brownian motion. Okay, here you have a walk 1, 2, 3, 4, 5, and it's pretty chaotic. And here again you have here time steps and time, and it follows here a pretty obvious random walk. And it can imagine also a particle or a walker in a park. So now we're going to go through the arithmetic Brownian motion with maybe different other characteristics, but it was very I think important to mention the random walk motion before going through arithmetic Brownian motion and geometric Brownian motion. Now, what we say is that the symmetric random walk is in continuous time approaches Brownian motion. What does it mean? It means that when you scale, the number of steps, and you increase, the number of steps in your whole horizon, you will have kind of, Brownian motion. So there is like a discrete, perspective. With the random walk, here is a continuous, approach with the Brownian motion, and you will assess that Brownian motion can be considered as the limit of, in fact, of the random walk, symmetric random walk, when the step size, tends to 0. Okay, you can approach that with the so, for example, the binomial model. So the arithmetic Brownian motion is a type of stochastic process that represents again a random walk in continuous time. So remember the arithmetic Brownian motion, because it's the random walk in a continuous time, and you will use that in physics and mathematics and many other fields to again model the stochastic process, okay, where there is a random component. And you will see that in the geometric Brownian motion, we will be the characteristic will be a little different, because of the possibility of having a negative value with the arithmetic Brownian motion. And here, what we say in the arithmetic Brownian motions, the linear refers to the fact that the change in the process over time is proportional to the time increment. Again, okay, the more time passes, the more your motion will accumulate this quadratic variation, and the more rough will be your motion. Okay. And in arithmetic, Brownian motion, you have this addition, of steps, of motions. So this is an additive process. And in geometric Brownian motion, it's geometric. Okay, so in geometric Brownian motion, we will take into consideration the compounding of interest. Okay, and so why we use the geometric Brownian motion, because it reflects, in fact, reality. The compounding effect of stock, increasing, and having also the possibility to model, only positive, increments. The mathematical representation of the arithmetic Brownian motion is this. What does it mean? This, I think all of you have seen this, equation. What does it mean? That D here mean for a small increment, the small increment of a very small increment of the price change is due to this part, which is the deterministic part, and here the diffusion part, which is in fact the volatility part, the random part. Okay, deterministic part multiplied by a small time interval. Okay, again, it's about the mu here letter. Quick letter, it reflects the expected return of, I don't know, stocks. So you will maybe, I don't know, 20%, 10%, or 15%. Here it's deterministic because it's constant, it's given. Volatility is also given. And here it's really pretty original. It's the winner process, okay, or Brownian motion, which will introduce randomness, or this uncertainty into the model. And the real problem is that you will see that since the Brownian motion is non-differentiable anywhere, but still continuous, you can't use ordinary calculus. Why? Because in ordinary calculus, you assess that the function you will differentiate or integrate will will be in fact differentiable. But here it's not differentiable. Still, we have to find a way to solve for this equation, and it's why you need the Ito lemma to solve this equation, because you can't use the classic chain rule of differentiating because of this random feature. And how do you assess that? You assess that because you will see that still it's really rough motion. There are no way to say that there will be a tangent over the the pattern or beyond. So it's neither concave, neither convex anywhere. And what does it mean? It's that mathematically you need another tool to be able to solve for the equation, and in the Black-Scholes model, it's what you will do by using the Ito lemma. But we won't do that today. Okay. So again, here the price change on a very small interval is dependent on the drifter, the deterministic term, the mu term, which is the expected return of your price here on a very small interval, plus the random part, which is the volatility, which is constant, multiplied by the Brownian motion process. Okay. Here you can see the arithmetic Brownian motion, and you can see first that it's you have time here again, and here you have the state where you are, and it can be a price or a walker, whatever. And what you can see is that it's there is a upward move, okay, upward sloping chart. And why? Because of mu here, which in the Python script was set at 20%, okay, with sigma at 10%, and still it's the deterministic part, like in an equation like the slope, and you can be you can consider that to some extent the way that it will drive the stock up, because the expected return is positive in here 20%. But still, there is this random part which will assess the volatility around the average of the or the the move of the stock. So the characteristic of the Brownian motion are continuous path. What does continuous mean? You don't you can follow a line, and it won't be a cut in the middle. It's what continuous means. Okay, it's continuous, but what is really it's really observable and really interesting is that it's not. We will see that again. It's not differentiable anywhere, like I told before. I said before. Okay, so the Brownian motion has continuous path. It means that the particle or the stock or the walker's position will change continuously over time. Okay, it means that it will contrast with the the random walk we talk about, because we are consider only discrete steps. So again, you have this random walk, symmetrical or not, which is discrete stochastic process, and with the Brownian motion, now you consider a continuous motion, but still very rough, okay, and again non-differentiable anywhere. The Gaussian increments, what does an increment means here? In fact, it's the difference between the two positions, considering two time steps. Okay, so it's Gaussian, so like the Gauss curve. And what does it mean? Is that the increments are independent of each other. It's really important to remember that they are independent of each other. So what does it mean here? The Brownian motion at t plus delta t, so delta t is an infinitesimal time interval, time step, minus the preceding position, if you want. So here is the increment, follow a normal distribution of 0. We know that because of this symmetric and this random part, which give us which tells us, sorry, that in fact, on average, you are supposed to be at the same position, and with variance of delta t. Okay. So what does it mean? It mean that over small time intervals, the particles position change by this amount that is approximately normally distributed, and the variance is time related only. Stationary and independent increments, we also already saw that for the random walk process motion, and it's a pretty cool property, because the Brownian motion is invariant under time translation. What does it mean? It means that if you scale up the time steps, so you decrease the time steps, you partition the time steps, you will have the same probabilistic behavior. Nothing will change in the way the process move, act. Okay, it doesn't change over time, and you will have also this feature, what we call that. I don't know if you read about Mandelbrot and fractal, and you know that he was challenging the the volatility, the constants of volatility and so on, and he worked on the Eston model about the river, the Egyptian river, and he assessed the fractal structure. But what does it mean, fractal structure? It means that in fact, when you scale down time and space by a given factor, it will yield another Brownian motion. So what does it mean? It means that here you have a snowflake fractal. What does it mean? That when you break your pattern the same way, a number of times which increase, okay, in number, you will get the same pattern everywhere. Here you have a snowflake. Here you have a snowflake. Here you have a snowflake that you can see. And what does it mean? It means that the Brownian motion is continuous, okay, but non-differentiable everywhere. So it's rough. Okay, it illustrates the randomness visually. So it's what fractal mean, but that is not, it's rough. You can't differentiate that. You can't assess the future steps, because when we differentiate, what are you doing? You assess potentially what the next point will be on your line, for example, or on your curve, because you can do that. Okay, because it's concave down, it's convex, and so on. So what the differentiable means on a practical, from a practical perspective, it means that you can assess when it's differentiable what will be in fact the next step. And when it's non-differentiable, what it means that it's so rough that you can't even have a guess about what will be your next, I don't know, Walker coin or stock price. You understand? And still, what it means also, because it's still regular, it means that things don't change. The probabilistic behavior won't change, even though you scale down the time. Okay, the time steps as many times as you want. So now we will go through the geometric Brownian motion. What's the difference between the geometric Brownian motion and arithmetic Brownian motion? It's this word, geometric and arithmetic. Arithmetic, in fact, is it's additive, okay, and here a geometric. Geometric, what does it mean? You multiply, okay? You multiply like you compound like interest, and it takes into consideration the reality of how price move, and you can make a killing in the market because interest compounding, okay. And it's a better way to model price price moves, because you take in consideration this feature, okay. And you need to take this feature, that means that which is to assess the continuously compounded return, okay, of a stock price over time, or financial instruments or whatever, okay. Again, the continuous return of the asset price is normally distributed, and again, the model takes into account both the drift and the randomness in the return. The drift, remember, what is the drift? The drift is the deterministic part, is the expected return of your stock, which is supposed not to change, and not to change, to be fixed on a given horizon, for example. And the randomness in the return, which is the volatility, which is assessed to be constant, like in the Black-Scholes model. So it doesn't change, but multiplied by this DT term, which is the winner process, our stochastic process. Characteristics of Brownian motion, the geometric one, stochastic process, again, continuous time stochastic process. It's random and it evolves over time. Non-negative values, why? Because GBM will ensure that the values will remain positive, because we will take the log returns, and we can't take the log of a negative number. It doesn't exist. And it's pretty cool property of log returns, because you can transform, you can accumulate that, and there is this transformation of addition into multiplication. Okay, so again, it allows us to consider both the normal distribution of returns, and also to assess the compounding effect, and also to to prevent us to form to get negative values. Still, in the future, you can have negative values, but it's the exception, not the rule. Remember the oil in 2020, I think, which went in the red territory for about 1 day or 2 days, I don't remember. So drift and volatility, again, I say it's the same as the two other stochastic processes. And what I've told different times and many times before, it's non-differentiable everywhere. So I think if there is something that you have to remember today, is this property, which is really, really paramount. It's where becomes complicated, and we need the math stuff because of this feature. Okay, what does it mean? Yes, it's I repeat it again. Yes, you can find a tangent to the path at almost the point, because it's too rough. Exponential growth, I've talked about that. Again, you have the Markov property. Remember, Markov is memoryless, and meaning that the future evolution of the process depends only on the current state, and not on all preceding states, and how it arrived at that state. Okay. And remember, exotic option who are path dependent. Okay. So it's why it's complicated to hedge more. It's more difficult to hedge, portfolio exotic option than vanilla option, because of this path dependent feature. Okay, memorylessness, again, Markov property. GBM is memoryless, like other stochastic processes, and it's why we use it's one of the the main characteristic you have to remember, Markov property, which the memory lessness, and also martingale that I didn't feature here, which is the fair game. I could have mentioned it again. So you see that it's the main feature, that you are now using a model that is a better fit to model stocks. Okay. And I made a little zoom on non-differentiability and quadratic variation stochastic processes. What is quadratic variation? It's a great stuff. We talk about quadratic variation, but sometimes we don't really have the grasp behind of the intuition behind quadratic variation, and I think it's really important to remember that. So here you have the formula, the math stuff. Here, what is it? It's the difference between two Brownian motions at the time step I plus 1 and here I and squared. What does it mean? Be careful. Quadratic variation is not it's not, it can give you a guess of volatility, but it's not the definition of volatility. Volatility, you made the difference between the distribution of your stock prices and the average, and you square them up, and after that you take the square root and you have the the sigma. Okay, but here what you do only is to square the difference between two positions, okay, of stock prices, and you square them. But why? Why? Because in fact, the main feature of the Brownian motion, or the stochastic process, it accumulates, in fact, variance with time. It accumulates because the more time passes, the more rough, volatile will become your stock. Okay, and variance is time, and quadratic variation is also time. So what does it mean? It means that since it's not differentiable, since it's rough about everywhere, on every time scale, you have to consider that the more time passes, the more you will accumulate, this roughness. Okay, and it's what quadratic variation means. And volatility would not capture this, accumulation, because here you have a summation. Okay, so it's really interesting, and you have to understand what quadratic variation means and why it exists here and not I don't know, in other for example financial instruments. Okay, you want to model, and especially we're talking here about contingent claims like options. And yes, here nothing to add here again. Why it's so important? Because quadratic variation is the measure of roughness, and if you don't assess the roughness, you don't assess the randomness, and you won't be able to hedge properly your portfolio of options. You won't be potentially able to trade properly, or I don't know, to assess your risk or whatever in your hedge fund, because of this feature, which is one of the main feature of the stochastic processes. And here, the geometric Brownian motion, you have this differential equation, which states a bit different. Here, a small variation, a very small variation of your stock price is independent of this drift term. Okay, on a very small time scale, multiply, okay, by the stock price, and here again the sigma, the volatility, multiplied by the stock price, and still this random component, the diffusion component, which makes it difficult to differentiate, or impossible to differentiate with ordinary calculus. You can use, and we will use that, and Ito lemma use approximation like the kind of Taylor expansion, but again here it's our component of randomness. So here, how we were talking about in geometric Brownian motion, we were talking about log returns. You remember? So log returns, and we say you have to find a solution of this differential equation, and you say where are the the log returns. So what you're going to do is differentiate that and take the integral of that, and that in fact you will divide by ST here everywhere, and you will get this formula, because by dividing by ST here, by ST will disappear, okay? And you will, what will remain is here, 1 divided by ST, and you will take, the integral of that, and you will get the log, okay? The log, because the log, the derivative of the log of ST is 1 divided by ST, okay? And it's how, a logarithm appears, and here is 0.5 multiplied by the variance is, the way to correct of the volatility, okay? And after differentiation, you will get that expression, which give you in fact the value of the future price with the compounding effect first, and here still with the random also component. So we'll finish with this Black-Scholes model. I won't differentiate this differentiate the Black-Scholes equation applying the Ito lemma. But when you want to hedge your portfolio, you start from the underlying, because when you use a derivative, you have, and when you tell derivative, you have to understand how the underlying behave, okay? Especially when you trade options. So you start with the stock price, and so the geometric Brownian motion, and after that you will differentiate that using what we call, the hedging portfolio. I wrote an article on that, how to differentiate, differentiate the Black-Scholes equation, stochastic differential equation. And in fact, here you can easily differentiate this part, but not this part. So you have to use the Ito lemma, and to be in the risk neutral measure, and use a hedging portfolio, and trying to replicate the portfolio you get, and by hedging it, okay? And after that, using the the Ito lemma, you will end with this equation, and obtain the famous Black-Scholes formula for a call and a put. Here is the purpose, not to make the calculation. It's just to understand that you start with the geometric Brownian motion we talk about, to take into consideration both the deterministic term and the diffusion term, and after that to use a special way to differentiate what you can't, because remember, the Brownian motion is everywhere continuous, but everywhere non-differentiable, and we need a special tool, which is the Ito lemma, just to give you the intuition. And you will end with this call option by creating a synthetic replicating a portfolio, which is the portfolio pi, which is the call minus a certain number of share, in order to get rid of this component, the diffusion term, so that you only have the deterministic term. It's how you do to derive the Black-Scholes model, and here you don't have this diffusion parameter. You get rid of that by assessing that you work under the risk neutral measure, where there is no randomness anymore, and that any asset it will earn the risk-free rate and prevent any arbitrage opportunity, like when you price. All derivatives are priced under the no arbitrage opportunity, so that the price prevent any participant to make money not taking risk, and getting at least the risk-free rate. So thank you very much. to all of you. Thank you, and see you next week for another class about quantitative finance made accessible.
Thank you so much, Florian.
My pleasure. See you.
See you. Have a nice day.
Bye. Thank you, Brian. Thank you very much.
Thank you, Brian.
Bye.
Yeah,
Bye.
thank you, Florian. Thank you, everyone. Thank you.
Bye.